Okay, dear colleagues, thank you for your bravery coming so early to our session. And I'd like to open our session on microwave technologies. And the first presentation will be exactly on that. It is MICROSTRIP antennas diagnostics. And presenter is Leszek Nowosielski. Is Leszek here? But the presentation is uploaded.
It's maybe yes out.
Should I do that? Until Leszek is coming.
Yes.
Okay, so the floor is yours. I'm just introducing now. You just find your slides.
Yeah.
MicroStrip antennas are the very convenient way to design the antenna with programmable directivity diagrams. But what is unusual in this presentation, but that diagnostics of these antennas is done using thermography. Thermography is the way to monitor the temperature two-dimension, to get the picture of two-dimensional distribution of the temperature. So I'm looking forward for your presentation. Please, floor is yours.
Thank you. I am not expert in thermography. I am expert in antennas, but it is very interesting topic from my point of view to test microstrip antenna using thermography. My name is Leszek Nowosielski. Thank you for your introducing my person.
It is back, forward.
Forward. No. Maybe this.
Okay. Maybe.
This short agenda of my presentation: introduction, antenna in radio communication systems, models of microstrip antennas, diagnostic of microstrip antennas with the thermography methodology, in conclusion. I will talk about microstrip antennas. The serious disadvantage of this type of antennas is limited power, load capacity. Because of small dimensions of this type of antennas, the power load is very small. The above limitation can be the cause of serious failures during the test of prototypes of antenna as well as in the period of microstrip antenna operation. Therefore, the suitability diagnostic is the essential element in the test process of prototypes as well as operation of such type of antennas. One of possible diagnostic method of microstrip antennas is based on using thermography. For different type of antenna, thermography is used for these goals. Within the method proposed, a distribution of temperatures recorded by the thermovision camera on the microstrip antenna surface is used for these diagnostics. The above diagnostic is based on verification of antenna parameters influencing local change of temperature distribution on the antenna surface. The proposed methodology of antennas diagnostic was discussed in my article. An antenna termination of the transmitting line is the element that should radiate whole power transmitted from the output of the transmitter. Because of the imperfections of antennas resulting from the production process as well as being formed during their operation, not the whole power is radiated in any working conditions from antennas in the form of the electromagnetic wave. This is obvious that the power losses of antenna in a considerable part are emitted in the form of heat. Considerable heating of the radiator in relation to other components of the antenna is a symptom of the impedance mismatching, because the power will mainly be dissipated by this element. In the case of mismatching, the input impedance of the antenna, a part of the power, will be reflected from the input terminals and returned to the transmitter. A higher temperature in the surroundings of input terminals of the antenna can be expected with the working conditions. Using this formula, I would like to mark that the range of radio communication depends on the antenna gain, and antenna gain decreases when the losses of power transmitted is big. For example, when this power radiates as a heat. So losses of the signal power resulting mainly from impedance mismatching have the effect to lowering a value of range, radio communication range in the radio communication path defined by the below dependence. Here is the gain power of the transmitting antenna. In order to investigate the temperature distribution on the surface of microstrip antennas, as well as verify its relation to the standing wave ratio at the antenna input, the three models of microstrip antennas were designed and made intended for operating in the frequency band 2.4 GHz. We have made three models of antenna. One patch antenna, two patch antenna, and four patch antenna. These microstrip antennas. In order to compare the temperature distribution on the surface of microstrip antennas, models made with the value of the standing wave ratio that has an essential effect on the power losses and therefore also onto the temperature distribution, in particular near the antenna connector. Measurements of standing wave ratio versus frequency have been done. You can see here the result of the measurements. This result of standing wave ratio in around the 2.4 gigahertz for single element antenna, two element antenna, and four element antenna. You can see that the antenna is working from 2.9 to from 2.1 to 2.9 gigahertz. In order to verify desing correctness and quality of work for the feeding system of the aerial arrays, as well as a radiator of models, don't expect of the standing wave ratio value measurement. Also, the temperature distribution measurement was carried out on the surface of three models designed. You can see here the model of one element antenna. You can see, it's working?
Yeah, laser is working.
Okay. You can see increased temperature in this area and near the connector. This is for 2.6 gigahertz, 2.3 gigahertz, 2.6 gigahertz. Of course, if the temperature is higher, the lifetime of this antenna will be shorter. You can see here two element antenna, 1, 2, 1, 2. It is for 2.5 gigahertz. Second picture is 2.8 gigahertz. You can see here that the temperature is very low around the around the patches. But the temperature is higher in these places, near the antenna connector. For four antenna, element antenna, 1, 2, 3, 4, 1, 2, 3, 4, you can see this is for 2.5 gigahertz, 2.8 gigahertz. You can see that we have problem near the connector. So we can suspect that the standing wave ratio in this area is very high. A temperature distribution on the surface of the microstrip antenna tested in the laboratory test stand setup was measured using the thermovision camera. The high frequency generator was used at the radio frequency signal source feeding the microstrip antenna. Because of low resolution of the thermovision antenna, thermovision camera, because this camera was very cheap this not high-level equipment. In order to increase eventual potentials of temperature distribution on the surface of microstrip antenna tested, the measurement signal was amplified by the power amplifier. The measurements were done at the ambient temperature 21 degrees of centigrade and at the distance of 50 centimeters from the surface of the antenna. The thermograms presented allow to state that the feeding system designate can be potentially the place of high power losses, and in the future it can be a potential place of antenna damage. Conclusions. Analyzing the results of the test carried out, it can be stated that there is dependence between the temperature distribution of microstrip antenna and standing wave ratio. This dependence can be observed by comparing the diagram of standing wave ratio with the temperature of the radiators as the function of frequencies. The minimal temperature for the single element antenna was achieved exactly at the same place where the standing wave ratio was the smallest one. In the case of antenna input terminal, the higher standing wave ratio, the higher temperature of the area. The above phenomena can be observed in situations when the antenna has been excited by the signal of frequency out of its working band. For these frequencies, the standing wave ratio is the highest value. As an effect of this, the most part of the power has been reflected and a considerable part of it has been changed into heat. Change of the maximal temperature are contained in the range 1.6 degree, but the change of average temperature of the antenna are maximum 0.9 degrees. Because of this reason, the thermovision camera used for this type of application should have the resolution not lower than 0.1 degrees. This is not very good equipment, so it is very cheap. The last sentences. Because of antenna geometrical dimensions, antenna considered of 2 and 4 elements are not able to become heated themselves to the same degree of the single element antenna. It is resulted from too small power delivered to the input terminals of such antennas. The input signal power for antennas of this dimension should be at least twice higher. And the antenna were tested in temperature 21 degree. It is better if this test will be done in lower temperature. In this situation, we can see differences, better resolution, temperature resolution. Thank you very much.
So we still have 1 minute for the questions. So please, somebody, Audrius.
What about temperature correction coefficient? Because with FLIR there is a problematic part, the correction coefficient. Because if it's black body, then it radiates 100%. But if it's different, it can cause the reflection, can cause the temperature increase in this metal part of the house.
What Audrius means that every surface should have its own.
I understand.
Have you taken it into consideration while doing this one?
No, because I am not expert in temperature cameras, but you can see here that if you use a very popular thermal camera and make the picture, you can see heated area. You have not to use the vector analyzer in order to measure the standing wave ratio. Only very fast measurement using the very simple camera, you can locate the area with the problems.
Direct
for
visualization of
very fast,
where you have the problem.
very cheap measurement tool for the location of the area with the problem.
Thank you. Thank you very much. Next presentation is on field uniformity and transverse electromagnetic mode verification in GTM 1000 cell. It is done by Audrius Merfeldas, but there are more authors here, so it is a whole team who made the job. So Audrius, floor is yours.
Yeah, hello, I am Audrius Merfeldas, as Linas presented, and now we will talk about the GTM cell and field uniformity and TEM mode verification in the cell. Okay, let's start from the GTM cell itself. Actually, it's like an antenna that works gigahertz transverse mode. In gigahertz transverse mode, it's like a strip line antenna that can radiate, and it can as well receive the signals. In this research, we are doing community tests, so we only radiating the device under test with various frequency signals. There is here you can see the laser is here. Here you can see GTM cell itself is the structure. I was measuring one reference plot here, and this one is RF generator that generates the RF signals, and it sends to this strip line. And here is the reference plane. I made a grid and I measure all the grid points to show the results. Why we need to measure field uniformity and why we need to measure TEM mode in the cell? Actually, we need to evaluate GTM cell performance and to know is it working properly or not for all the tests. That makes the test reliable and more reliable. Evaluating GTM cell aging. Actually, the GTM cell is aging and the shielding, all the equipment is degrading, and that's what it caused the field uniformity problems. And spotting and troubleshooting defects. The standard states that we need 75% of the whole reference plane to be uniform from -0 to +6 dB. That means we need to have at least, let's say, 10 volts per meter, but we can have +6 dB more, but not less. Okay, and here we have a small video where I'm sweeping all the frequencies from 30 megahertz to 1 gig. And actually you will see in some frequencies there are some spots here. That is the higher field strength, electric field strength. And at the higher frequency you will see very interesting results. Now the frequency is higher and higher. Yeah, and it's finished at 1 gigahertz. And now we will investigate it a little bit more. Here I measure the center point of the reference plot. What we have? We have EY, that is electric field. Y projection is the wanted field that we need. And all those EZ and EX is parasitic fields. So actually we need to have as lower as possible. Now what we have a standard stated reference plot. It's around 300 millimeters times 300 millimeters. And we have results here. As you see, there is a fluctuation of the field here. And up to 300 megahertz, it's quite stable. Later, and actually it depends on the cell itself, because here it's working on the 50 ohm resistors, and here the absorber is taking place. So actually the absorbers is more sensitive to any imperfections of the cell. Here we have the same reference plot, and as you see, EX, that means parasitic field in x-axis. As we see, there is a one big spike. This is not very good, but it's not problematic because as we saw, it's 75% should be as low as possible. So actually normally it goes below the 6 volts per meter. While having EZ is a little bit higher, and we have some spikes there, but still it's quite okay. And now let's investigate in the 2D plots. As we see at 30 megahertz, the lowest frequency range, we have very uniform field here where we're measuring, but for higher frequencies, the field uniformity is a little bit degraded, as we saw on the previous slides. For parasitic fields at EX, at 30 megahertz, we have only those corners where actually the septum plate is here. So we have at the corners quite big ununiform area, but the central area is very uniform. For 1 gigahertz, it's a little bit, uniformity is not so good, but actually we need as low as possible this field, so as you can see, it's quite okay. The same with EZ axis. EZ axis is a little bit lower as well, and it works the same. At 30 megahertz is very stable, but for higher frequencies it's reflecting as well the currents in the septum plate. And now I plotted some plots about the whole area of measurements. So actually, if we measure the whole area, the whole cross-section of the GTEM cell, we saw that EY, that is wanted field, is very similar to EX, that is parasitic field. So actually we can't work at the whole area of the GTEM cell, but if we saw the standard stated 330 millimeters times 330 millimeters plot, we saw that EX is very low, actually it's lower than 5 volts per meter. EZ is a little bit higher, and here we have the red is minimum and the blue is maximum. So actually, as you can see, there is all the nodes measured were falling between those curves. So this situation is quite good. Okay, now what we have, the standard stated that we can measure a little bit bigger width of the reference plot. So here is a little bit difference. I will show you. If we move from this to this, you see the EX is increased. Okay, and now let's summarize the presentation. Field was measured in 3 directions. It's fully enough to represent the TEM mode and quality of the cell while measuring the uniformity of the field itself. Field uniformity is more stable up to 300 megahertz. As I told, it was working on the GTEM cell is constructed like that it's working on the 50 ohm resistors, but for higher frequency absorbers taking place, and it's much harder to prevent all the reflections inside. And unwanted field components are stronger, closer to the GTEM cell walls and all the imperfections. Okay, so thank you for your attention and questions.
Please,
For field strength measurements inside the GTM, you have used a sensor.
Yeah, isotropic probe.
Isotropic.
Yeah.
You have used a scanner, mechanical scanner, or have used?
No, I done it manually because all any parts of the scanner, even if it's wooden or plastic, it caused the imperfections of the measurements, because the epsilon is different, and you know.
How much time it takes to?
Yeah, it was quite long experiment, and actually sweeping from 30 to 1 gigahertz is automatic for us, but we need to manually place this. So actually it takes more than 2 days, I think.
And the last question, this type of measurement is needed for immunity testing.
Yeah, because
according to the standard, so it is obligatory for accredited laboratory to make this.
Yeah, and each laboratory should make it, because if you do immunity test, let's say if we have device under test and we need to measure at 10 volts per meter, and we have 10 volts per meter here, but we have 5 volts per meter there. So actually we can't, cannot investigate.
More questions, please? Because of the same reason it was mentioned before, G10 cell is most useful in immunity testing because it is easy, the power cell. I missed what was the power used in your investigation.
The power is stable all the time, actually. So I made one reference measurement and I fixed the power. And later I was doing the same power, sweeping through the frequencies with the same power. So then I can investigate how the field immunity is.
No, my question is, what power was used?
What power was used? It was about 25 watts. But it depends on the frequency because it depends on standard wave ratio.
And what powers you are expecting to use? At this level? Much higher?
No, at this level.
At this level.
Because it was, as you see, it was about 10 volts per meter, so
Yeah,
it's high as the standard. The highest level is special, but 3 volts per meter, 5 volts per meter, and 10 volts per meter.
Thank you.
Mhm.
More questions? Thank you, Audrey. Next presentation is on indoor channel modeling. And the modes considered are CISO and massive CMO, probably so, in the 60 gigahertz millimeter wave band. And the presenter is Boris Yüksekaya,
Yes, exactly.
United Kingdom and Turkey joint work. So Boris, the floor is yours. All presenters fitted into 15 minutes, so please the rest keep the same.
Okay, I'll try to. Hello everyone, I am Barış Yüksekaya. I come from Hacettepe University, Turkey. I was in Imperial College London for the last year and we worked about millimeter wave spectrum and the telecommunication applications in this area. I'm going to talk about the indoor channel modeling that we have done in simulation for single input and single input, single output and single input, massive multiple output channel scenarios. I guess this one isn't working. I'll give a brief introduction and give the system model. After that, I'll talk about the ray tracing procedures that we have done on the channels to model the channel and sum up with the results and future work. The number of wireless devices accessing wireless networks around the world is increasing rapidly. As we all know, we all have smart devices and we use these devices to reach the information that we need through internet or other networks. And new technologies and solutions are needed to provide higher data rates because we all need more data. For example, with the introduction of 4K videos, the data rates nowadays isn't actually allowing us to watch these videos in a perfect way. So we need 5G, maybe later 6G, and we need new technologies that takes quality of service constraints like interference into account. For example, the carrier frequencies that we use today are usually under 10 gigahertz. But in the next generation, 5th generation communication systems, it's expected to move upwards. For example, to 60 gigahertz band, which is called millimeter wave systems. And there is a spectrum range that can be used up to 7 gigahertz in this band. And there are some applications that use 1 to 2 gigahertz of spectrum bandwidth. Let's talk about the advantages of the millimeter wave. As I said, it has a wider bandwidth. There are some applications that use 1 to 2 gigahertz, and you can use up to 7 gigahertz in theory. And it has lower interference because there are not so many applications in this band, and this means there are less interferers. With the increased carrier frequency, the wavelength is small, so we can use small antennas with small distances between these antennas. So we can use massive number of antennas in a very small area. Of course, there are some disadvantages. For example, the penetration through walls for this band is not known perfectly, so we need more channel models. And we know that the free space path loss, the loss due to oxygen and rain, is higher in these bands. So we need to make new structures for the receivers and transmitters. And of course, the smaller parts of these antennas costs higher. Despite the importance of millimeter wave, there is a lack of generic 60 GHz channel models for wireless channels. And the main purpose of my research is to perform two-dimensional channel modeling operations in the 60 GHz millimeter wave band. I have used ray tracing with image mirror image technique in order to find the reflection paths, in order to find the multiple paths of the channel. And I have investigated the characteristics in terms of multipath delay spread and multipath power content. This system model is a basic 5 meter by 5 meter room. In this work, I have only considered two-dimensional channel modeling. As a future work, three-dimensional channel modeling in a real-time network is considered. We have a transmitter and a receiver. The transmitter has a single antenna and the receiver can have one or a massive number of antennas. The channel impulse response is found by generating the geometry of the reflected paths, and all of the paths are summed to find the channel impulse response. All of the paths have channel gain, which is the inverse of the losses, and we need their time delay information and phase information. For example, let's have a look at the figure on the left. We see the line of sight path, which is a direct line between the transmitter and the receiver. And on the right, we can see an example for the first order reflected paths. First order reflected path means the signal is reflected just one time from the walls, and we can find the distance covered as finding the mirror image of transmitter, and the distance between the mirror image to the receiver gives us the actual distance that the signal covered, and also we can find the reflection angle to find the reflection loss. Then we should find second order reflection points, and we can find this by taking the mirror image of the first mirror image that we have found and the distance between the TX double prime, which is this second order image, mirror image. The distance between this TX double prime to RX gives us the distance that the original signal covered, and we should use the reflection angles to find the reflection loss as well. So if we do these procedures for all of the paths that can be found, we can find the channel impulse response geometry of the scenario. And here we have one line of sight path, 4 first order paths, and 6 second order paths. The sum of all of these paths and their characteristics actually gives us the channel impulse response. Here we can see the line of sight, first order paths and second order paths as the channel impulse response. And we can see that the delay spread is on the order of 30 nanoseconds. Therefore, the coherence bandwidth is 33 megahertz. I said that the bandwidth that we used is on the order of 1 to 2 gigahertz. So the channel, for the indoor channel, we can say that it is frequency selective. So we need to use equalizers or orthogonal transmission in order to combat with the frequency selectivity of the channel. And on the right figure, we can see the power percentage of first X multipaths. What this means? This means that first 2 multipaths have almost 95% of the power that is included in the channel. Or the first 4 multipaths have almost 99% of the power that the channel has. So this means that we can neglect the second order paths, because these paths doesn't contain 1% of the power that is included in the channel. So in next channel models that are to be done, the line of sight path and the first order path should be considered. I guess we should talk about the single output, multiple output scenario right now. It is the same, but now we have more antennas in the receiver. In this example, I had 100 antennas, and the distance between each antenna is 2.5 millimeters. We have the line of sight components again, which are direct lines from the transmitter to each of the antenna. And we have first order reflection paths, again 100 paths for each first order reflection. And we have again the second order paths, 100 paths for each antenna. And the channel impulse response geometry is as shown. This time the channel impulse response is a matrix. It's a matrix with the size antenna, the number of antennas times the number of multipaths. And for a reference antenna of the receiver, we can see the impulse response. Again we have a delay spread of 30 to 35 nanoseconds. So this is a frequency selective channel. And again we can neglect the second order paths in order to find the modeled channel. And even if we neglect these parts, the delay spread will be on the order of 10 nanoseconds, which again means a frequency selective channel. To sum up, this study tries to inspire an understanding of the characteristics of indoor 60 GHz millimeter wave band. I have aimed to overcome the lack of generic 60 GHz channel models for SISO and massive SIMO. The channel models were created using a ray tracing method with mirror image technique. And we found that the length of delay spread showed that the channels are frequency selective. So our next work should be working on the equalization techniques for millimeter wave bands, and also maybe considering orthogonal transmission again in here. Other simulations show that the dominance of loss path and first order reflection paths over second order reflection paths. And we can see that 100 antennas can take so much a small place in this millimeter wave scenario, and we can use this massive number of antennas in order to increase the array gain and receive antenna diversity gain. As a future work, as I said, a scenario will be constructed in real time, and real-time channel coefficients will be calculated using channel analyzers in 3 dimension, of course, and I'll be constructing next generation receiver and transmitter structures also. Thank you for listening to me. It was a pleasure to be here.
Now, questions? Does anybody have questions?
I know it will be hard to ask questions because I work on the resource allocation part of telecommunication, and this maybe is about antennas.
I have a question. I was expecting that there will be more letters in your title, because you told CISO, it is
Yes.
clear, single input, single output.
Yes.
Then SIMO, single input, single output, multiple input. But why not to go further by more?
Yeah, it will be.
What was the obstacle that stopped you? Because the technique is quite simple, ray tracing, you do not care about how reflection is occurring.
Actually, it was because the lack of the space, maybe. The MIMO is straightforward. If you can do SIMO and SIMO, then it's obvious you can. It is trivial to do MIMO. So it was just maybe more information, but less knowledge.
Can I ask one more question?
Yeah.
When you model the reflection,
Yes.
what is considered, or you just consider 100% reflection?
No, For the reflection, we thought that I thought that the walls are plaster, and I took into account the reflection angles exactly, and these reflection angles change the loss caused by the reflection.
So
And
the rule
also-
is very simple. It doesn't matter which wall you are hitting. You still consider it as plaster.
Plaster, yeah. For
And,
indoors,
then
generally,
you just use-
generally in the literature, it's taught as plaster for indoors. For outdoors, of course, it's different, and there will be future work.
Okay. More questions? Thank you. You have saved some time for next
Thank you
presentation.
very much.
Okay. You can see that we are covering all areas of telecommunication. And once we went into communication, next presentation is design and modeling of an enclosed array of square spiral antennas for microwave tomography. And the presenter is Milos Subotic. So the floor is yours.
Okay, I'm Milos from University of Novi Sad from Serbia. And first of all, what's the subject of this paper? It's about a microtomography. I just showed it is, you have one antenna which transmits electromagnetic millimeter waves of radio waves, and they are scattered by some object under scanning, and these scattered waves are measured with other antennas, and you have input, you have output, but you don't know the electric distribution, don't know function of that problem. That's inverse problem. It's a hard optimization problem with multiple solution, and because that it is hard problem to solve. And what's interesting to find out in the literature that actually resolution and quality of resulting image doesn't depend on the wavelength or used waves, such as the case in the radars or telescopes similar, but it depends on measurement noise and modeling errors. And what we wanted to do is to make a better design of imaging chamber and antenna array to make these modeling errors and measurement noise lower. So just a short review, there is all kind of antennas used in this field, and what's the important is that in simulation used in inversion, most cases antennas are somehow approximately modeled, like point source or line source or plane wave. And also the chamber with antenna array is also approximately modeled. It is usually just array placed in one plane, and only 2D tomographic image is obtained, and that is completely ignoring of 3D nature of propagations and scattering of electromagnetic waves, and 3D nature for radiation of waves from the antennas. But there is a few 3D versions as well, but they are not so popular, mostly because it is much slower for inversion, much slower for calculation. Also, what is interesting to mention here is that in most cases chambers are filled with some matching lossy fluid. It is used to match the impedance between antennas and object under imaging, and also it lowers the multipath which occurs in a chamber, and that multipath mask scattered waves from the object, which make additional problem in the imaging algorithms, but it has additional attenuation. Also, in some cases there is a metal wall around the chamber, and in some cases there is no, and in many cases outside of the imaging region it's not modeled like antennas themselves. And so the summarized constraint which we had in the designing, we wanted to make a precise modeling of the chamber and antennas and array. We wanted to have a larger number of antennas which could help inversion, Also, we wanted to lower the mood path and wanted to lower external interference. So our solution is based on these 4 points. First, we selected square spiral wire antenna because it is easy to model in finite difference time domain simulator. It could be modeled like simple wire, and it could snap to the Cartesian grid of the FTDT, so it's really easy to precise model that antenna. It is also wideband antenna, and it has a low radar cross section. That means it has a low reflection to the chamber, which could be problematic in the near field imaging of microwave tomography. Also, we make methodology to interleave antennas one behind the other, so we can pack more antennas on the same space and to have better inversion in the future. And we introduce absorption wall around the imaging chamber to absorb reflected rays from the chamber wall. The material should have a low permittivity to have low reflection and to have high losses. And for example, wood, some softer wood would be really good for that purpose. And also we put metal shield around the imaging chamber to lower external interference. And this is how it looks like. It has a metal shield around the chamber and absorption wall on the metal shield, and on the sides of the chamber there are antennas, and they are, as you can see, interleaved one behind the other. There is a feed to the outside of the chamber, and inside the imaging region there is some kind of phantoms and object under interest. And this is how those square spiral antennas looks like with their interleaving one behind another. And we modeled that and simulate in FTDT simulator and compare with one 3D imaging solution from the Wisconsin Madison Research Group. They use the patch antennas, and first of all they have 28 antennas and we have 100 antennas in our solution. That's 4 times more antennas approximately, and also it is interesting to know that our solution is faster than their solution, simply because patch antennas need finer details and they 1 millimeter grid, and we can work in 4 millimeter grid, so that lowers a lot the space of calculation. Also, it is interesting, we compared different solution, and for example our solution with the fluid without absorption wall is a little faster than a solution with absorber wall, because it's with absorber wall chamber is larger. And also we compared measured signal. It is interesting that even if that there is a nicer fidelity of that signal with less smooth path in the case with absorber wall, then when we have a fluid, a matching fluid, lossy fluid in the chamber. And to summarize conclusion, we made measurement chamber designed and simulated and compared with other solution, and what's the novel is that we use that square spiral antennas and absorption wall. It could be shown that square spiral array has better performance than a patch array, and the chamber is with fluid is a little faster, but chamber with absorption wall have better performance. And what we potentially have with our solution with square spiral antennas is that we could have a larger number of antennas and higher bandwidth because wideband antennas. But the future research direction, it is better modeling of materials used, not modeling just on one frequency but in the range of frequencies, than the thin wire model of for antennas in FTDT, on the then better overlapping scheme for antennas to make even denser antennas array, and to use more realistic, anatomically realistic phantoms, because microtomography mostly used in biomedical applications, so it is better to have some real part of body like scanning to have realistic situations. Also, we want to apply truncated singular value decomposition method, which could be found in the literature to comparing this array for microwave tomography. And also we want to make this chamber to cross the gap between real life and the modeling. Thank you for your attention.
So now we have a time for questions. Please.
I would like to ask, why you choose this rectangular shape instead of more common rounded shape?
Because it is easier to snap to the grid of FTDT algorithm, because it has Cartesian grid, and you can draw the wires snap to that grid. If we have around spiral antennas like usual one, we couldn't easily model it. There are some papers that could model arbitrarily directed wires in the FTDT, but it's much complicated modeling. And we, in previous papers, we explicitly choose square spiral antennas just because they are easily modeled in the FTDT.
Thank you.
May I ask the question?
Yes.
Mine is similar to Jan's. Why have you been considering slot antennas? They are easy to fit, easy to simulate. They will stick to your grid.
Well, I think that we consider some certain antennas. Maybe Vivaldi antenna is a typical one used in these applications. But Vivaldi antennas has curves which are not so easy to model in FTDT again, and we consider took some approximated Vivaldi like to be square more. But again, for example, Vivaldi antenna occupies much more space in the imaging. This antenna, square spiral antenna, is perpendicular to radiation, so you can put it on the wall of the chamber, so it doesn't occupy too much space. Vivaldi antenna is transversal, so it will be occupied a lot of space and a lot of simulation resources, even more than phantom object of interest. So that's the reason why we again prefer patch antennas and these antennas.
More questions? What is the essential application? Yes, I have understood that it is tomography, and in the future it will grow to two-dimensional arrays, so it will be a three-dimensional reconstruction. But what is the application that you are looking into? Human being,
like something like that.
Oxygen distribution in the human body.
The most interesting is biomedical application. There is some non-destructive evaluation of materials and ground penetration, things like that. But biomedical application are most interesting, and they are very good for discovering cancer in comparison with X-ray, CT. And CT is also the dangerous, and it is cheaper solution than, for example, MRI, which is quite expensive.
Yeah, but you will lose resolution.
Well, that's the ongoing project of the many people, so it is going down there. In most cases, resulting images, what I found in the literature, are not so good, and in any case, you need a trained radiologist to look on the pictures and to say, oh, this looks like it's not like that you usual somebody which is not trained to can decode these pictures.
Thank you. Very interesting. My knowledge ends up here, so I'm not sure whether authors are present or not. So please indicate whether you are here or not. Georgios Konstantinos Koramis or Apostolos Dimitrios Kotopoulis, Evangelios Dimitrios Kalitsis. Yeah, that's Panayotis. No? Panayotis is not here. Okay. And what about the next one? Low complexity spectral partitioning based on music algorithm. Yes. So your slides are not there, yes?
Yeah.
So other presenters saved you 3 minutes, so please be fast. Just a note, because we have some time until next presenter will upload his data. Just looking here. I have noticed that despite this high frequency fields, a lot of applications go into imaging. You see it? Many applications of radar, and even the one that we missed from Panayotis Frangos, it will be radar, and just one was in communication, despite everybody is saying that we will be missing the technique for communication soon, because the amount of data that we need is growing, and we need to solve it somehow. You ready?
Yeah.
So floor is yours, please.
Good morning to everyone. Thank you for inviting me to present my paper, The Low Complexity Spectral Partitioning Based Music Algorithm for Automotive Radar. I'm working for DIGIST in South Korea. My name is Sang-dong Kim. My agenda is composed of introduction, system model, and conventional and proposed algorithm. And last things, we show the simulation and experiment result. As you can see, radar is used for automotive radar. Some kinds of the advanced cruise control and autonomous emergency braking and lane changes assistance and blind spot detection. All kinds of the application is very so much useful for the automotive, especially when the driver want to change the lane, the driver want to change some kind of situation in the road situation. This sensor is very useful. Especially our research institute is focused on to make the joint blind spot detection and the lane change assistance for radar system. The blind spot zones is under the 2.5 meter, and the lane change assistance zone is under 30 meters. We did the design and implementation and verification for the automotive radar. Before understand the automotive radar, we need to understand the radar signal processing trend. The 1990s, analog radar is used for the pre-series and the SAW filter. And on the 2000, the digital radar is used for detailed the Fourier transform and data beamforming. On the 2010, the Kappan and linear prediction is used for the high resolution radar. These days, the music and the Esprit algorithm is used for super resolution algorithm. The music means the multiple signal classification. Estimation, Esprit means the estimation of signal parameter via rotational environment technology. This radar trend is for the more resolution. In aspect of resolution, we can show that the music has the better performance than the FFT. However, the conventional vehicle radar is the top maker, the Infineon in German. That they use the key algorithm as the DFT to detect the angle and velocity and the range for the FM the radar. So we need to suggest high resolution, super resolution algorithm for the future radar. If we under the super resolution algorithm, we use the system model like that. The transmitted signal use this linear chirp with a rectangular window like that. The chirp is change the frequency, the low frequency to high frequency like that. The in RX part, we use the dechirping the process. The dechirp process means that the transmitted signal is multiplied by the received signal. Finally, we can obtain the sinusoidal signal. The frequency of sinusoidal is proportional to delayed time. Using a received signal, we can obtain the conventional super resolution algorithm such as the multiple signal classification. The received signal is obtained the autocorrelation function. Using the autocorrelation function, we can obtain the eigenvalue decomposition. We use the noise eigenvector, and the signal subspace is the orthogonality. So we can obtain the sharp spectrum like that. When we have two target like this, DFT cannot resolve, but the music can resolve like that. The second conventional algorithm is the spectral partitioning, the super resolution algorithm. This algorithm goal is to reduce the noise power. That algorithm is composed of DFT, spectral partition window, and the inverse DFT and the super resolution algorithm. Using the frequency spectrum, and spectral partition window is applied to that using a S band. Finally, we can obtain the inverse DFT. We can obtain the low noise, the received signal, and to obtain the fine frequency, we use the super resolution algorithm there. However, the conventional algorithm has the logic computation load, so we cannot apply to the embedded system for automotive radar. So we need to make the proposed algorithm like that. The proposed algorithm composed of a signal-based spectrum partition part and efficient spectrum generator. The DFT and the spectral partition window is the same as the conventional spectral partitioning. From this part, the proposed algorithm is showed. Among the window of the signal, we can choose the signal-based window using the threshold level, and the signal is changed by the inverse DFT. We can obtain the low noise based on the signal-based the window the signal. So finally, when we use the music algorithm, we can find the low complexity the spectral partition music algorithm the result. That result is similar as the spectral partitioning, and the complexity is very low. Using the DFT, we can obtain the frequency range. The frequency range is applied to the S-band window. And using the comparator and the threshold level, we can obtain the signal-based the window data, and we store the only signal-based data. And using the inverse DFT and the music algorithm, we can obtain the low complexity. The proposed algorithm required processing time is like that. The proposed algorithm is similar as the music algorithm, but the spectral partition algorithm, the complexity is very higher. We can measure by speed time of MATLAB. To verify the proposed algorithm, we use the Monte Carlo simulation, over 10,000 estimation. Two targets were placed the 5 meters and 5.8 meter. When we have a single target and SNR minus 22 dB, just the proposed algorithm and the spectral algorithm just only one target detect, but the music and DFT cannot detect. when we have two target at SNR 10 dB, proposed and the spectrum partition algorithm, the resolved like that, that performance is better than the music and the DFT. Even the DFT cannot resolve we have two target. In aspect of Newton scale, the error and the detection probability, we have the similar performance than the previous part. To verify the proper algorithm in real channel, we use the chamber room data. We have a chamber room frequency range from 8 GHz to 110 GHz. The dimension 10 meter length, 5 meter width, 4 meter height. We made the RF system like that. The frequency range 24 GHz to 24.0 GHz, and output power 8 dBm. The overall noise figure is 8. We can obtain the similar result proposed the spectrum algorithm, the spectrum partitioning, the music algorithm and music and the algorithms. All algorithm, the performance is similar, but the proposed algorithm has a less complexity. So we know that we make the low complexity spectrum partitioning music algorithm. To apply the proposed algorithm to automotive radar, we can see the specification of automotive radar. Set the frequency 24 GHz, for blind spot 5 meters, lane changes assistant is for 80 meters. And the algorithm is embedded here. The algorithm, the RF system is similar as the previous page. And this part proposed the signal process parting. We use the Texas Instrument TMS 320F28-335 chips, and our algorithm is embedded here. We did the experiment here. The moving target is up and down the moving, and the radar is fixed. The result, the GUI is obtained to obtain the distance and velocity and angle of the object. As you can see, some kinds of position we can obtain the radar signal detection, the range velocity map and range angle map and 3D map. And last, in real situation, the environment, we use the experiment. We obtain the clutter and the moving target, all kinds of things. But we have the remove the clutter algorithm. We obtain just only the moving target in the real situation. This algorithm is working under the 50 milliseconds in the embedded system. We have a proposed low complexity spectrum partitioning music algorithm, and the proposed algorithm consists of the DFT, the comparator, the memory, inverse DFT, the music algorithm to certify the required accuracy and reduce the complexity to embed the automotive radar system. And time delay the performance, we did the multi-targets AW channel, the Monte Carlo simulation. Finally, we can know that the spectrum partitioning algorithm and the proposed algorithm is similar to performance, and the complexity is the proposed algorithm less than others. The proposed method is applicable to vehicle radar due to its low complexity characteristic. Thank you for listening to my paper. Thank you.
So, any questions to the author? Jan, please.
I can ask one. I saw that you used linearly modulated circuit in your system. Have you considered also use of maybe non-linearly modulated circuit? It would be more energy efficient.
Yeah. You asked me the non-linear the chop system.
Yeah.
Yeah, but especially we use the VCO, the voltage control oscillator, to make the linear chop. But to make the non-linear linear chops, we use the DDS chip. The seems like the FPGA, so it is very higher complex price. So we cannot apply it there. So we just only use the linear chop. Yeah.
Very good question. Anyone?
How did you compare your computational complexity to the conventional procedures?
And which ones you consider conventional? DFT, music?
Yeah. We compared the music and the spectral partition and compared, but this table is not included the DFT. But maybe it seems like the DFT is similar as proposed. The DFT is lowest the complexity, but DFT cannot resolve the target. It seems the very lower target. So the music and the proposed algorithm is just applied to automated radar.
And you compared using the CPU time of MATLAB.
Yeah, right. In the computers, because in embedded system is a little difficult to measure the processing time. So just only use the computer. Yeah.
You mentioned some kind of super resolution algorithm.
Yeah.
Am I right?
Yeah.
May I learn the name or explanation why you have to do that in the super resolution algorithm in this process? Why?
I don't know exactly. Maybe some the previous paper so-called the superledger algorithm, multiple signal clarification and the S-split. So I don't know why they call it the superledgeration. Maybe it is very the highlight. yeah. I don't know. Yeah,
But
exactly.
probably your question was different, yes?
No, actually.
Why you need super resolution?
Yes, I want
Why
you
you
need to use
why?
super resolution.
Yeah, because the automotive radar is need to more the resolution because now just only the radar detect the angle and the range, but the later especially military using the radar we want to obtain the microwave imaging so we need to improve the resolution. So maybe the automotive radar is also need to finally go with the imaging radar.
Jan, you have questions.
Yeah, I have second question about the Fourier transform. You used conventional Fourier transform, but have you considered also use of different ways like circuit transform? You can use it instead of multiplying by sine and cosine. You just can multiply signal by circuit, and it is more efficient. You can do it more faster, and become more faster. Circuit transform.
Yeah.
You can read about that.
And besides, DFT is objected by the grid. With DFT, you have to be fixed to the grid in order to estimate the frequency, which is related to the distance. But with the chip transform, you are free from this disadvantage. So the question that Jan gave you is yes, because remember, Jan, Kim told that the essential reason why they discarded the DFT was that it is not giving the resolution. Actually, it may be so that it is giving the resolution, because if you are able to estimate two different frequencies, you have the resolution. But more or less, they consider it as not giving the resolution, and then they go into super resolution algorithms, because the bandwidth that you are using is
we have 200 megahertz
less than you would like the resolution to get. Therefore, once you consider that your signal-to-noise ratio is good, because that's the obligatory condition for super resolution algorithms, they go into super resolution. But Jan's question was, okay, so DFT is discarded, but there are other techniques that can still use the frequency domain, like chip or chip Z transformed.
jet transform, yeah.
Have you been considering those?
But I think the jet transform and the DFTs, I think the performance is similar, but the music algorithm has a very powerful advantage. Just only use the software algorithm to obtain the higher, the 2 and the 30 times the better than the resolution. So maybe, we focus on the make the super ledger algorithm. Yeah.
I understand. Yeah.
Yeah.
Maybe this our algorithms will not fit so well with these music algorithms. Maybe it's the reason. But still, it would be more efficient and much faster. And needs more resources for computation also.
It will be not computer, I understand. It will be FPGA.
The final goal is that we embedded the DSP, but this part is just to measure the processing time. We used just only computer. Finally, we used the embedded system to measure the processing time. Right?
Boris had a question.
Yeah.
Boris, please. Oh, you forgot already?
No, I didn't forget, but almost the same question. So
Any more questions? The area is quite interesting, and we still have time because we have killed one of the presentations, so still 15 minutes to go. I guess that if anybody has questions, so there is a coffee break, so you can do this during the coffee break. Thank you, Kim.
Yeah.
And actually.